Hello everyone. So in the previous sections we learned a lot of new reactions. We learned about aldol condensation, Claisen condensation, Diekmann condensation, and what else? Michael addition, conjugate addition. Okay. Now you can see in this molecule there are two rings. So by starting with two compounds, we can make a new ring attached. You will see a lot of organic molecules have ring structures. For example, cholesterol has 4 rings, and many natural products have many rings in it. So it's a good thing to know how we can make rings, okay, when we are synthesizing a product. So the Robinson annulation, that process form a product with the 2 cyclohexanone rings. As you can see here, you will see this is a cyclohexanone, and we can react it with the alpha beta unsaturated carbonyl compound. So this is called Michael addition. Remember, if you form enolate adding onto the alpha beta unsaturated compound is called a Michael addition. Now here you have a hydroxide, OH minus. So this can go and grab a proton. This is acidic hydrogen, and give its electrons to this carbon, okay, and also can form the enolate. So this will create something like this, O minus, have the double bond right there. So once the enolate is formed, you can see once you form the enolate, this enolate can react like this. Enolate is adding onto the alpha beta unsaturated carbonyl compound. We learned this reaction. This is the Michael addition. Okay, so this will give you a product like this. So you have your ring, and then you have the double bond oxygen carbonyl group, and we can number these atoms. If this is 1, 2, 3, 4, and from the other carbon we can number, if you start with carbonyl group, 1, 2, 3, 4, 5, 6. Okay, so then this is going to be your number 1, number 1, number 2. So the second carbon is going to form a bond with the first carbon of the alpha beta unsaturated compound. So for the number 2, you're going to be attach number 1 of the other group, and 2 and 3, and then you have another one, a methyl group 4. So you will have 1, and between 2 and 3, so this is 1, 2, 3, 1, 2, 3, no, they're too close, 1, 2, 3. So between 2 and 3 you will have a double bond, and on the third one you have this O minus, and this is the 4 from the from this group right there, and then this can reform the carbonyl group like this, and then grab a hydrogen H plus, so it's going to reform the structure carbonyl group over here, this one, methyl group, and that is this group. They are the same. Okay, now you form this part. Once you do that, you add a base. When you add a base, now we can do intramolecular aldol addition. Aldol addition is alpha hydrogen can be removed from the base. So in this one, our alpha hydrogen is going to be So this is the carbonyl oxygen, carbonyl carbon, and this carbon, they both are alpha carbons. But if you want to make a ring, so it will deprotonate from this one. Remember, 6-membered rings are more stable than 4-membered rings. So hydrogen will be lost from here. So we know there are acidic hydrogen. There are 3 hydrogens. So when you add base, this OH minus that we have over here, I can use, maybe I can use a different OH. OH minus acting as a base can take this hydrogen and form a anion, giving its electron to this carbon. You can form a anion there. So we have studied these steps before. Now we are putting them together. So when you do that, you will end up having a negative charge right there. And this can attack the carbonyl carbon and form a new bond. And that will make it, so a new bond form over here, O minus. Okay, and then when you add water to this one, you're gonna get this product, adding water, protonating this O minus. Once you get this product, okay, this one, and then the dehydration will lead you to alpha beta unsaturated carbonyl compound. So the hydrogen from here and then the OH will lose as a water molecule and then form this. Okay, so for the steps in the Robinson annulation, is first step is the Michael addition, and then the intramolecular aldol addition, and then removal of the water molecule. Okay. Now similarly, if you have other molecules like this, so you can see how the retrosynthetic analysis take place, meaning how can we go backwards and figure out what should be the starting materials, which is a retrosynthetic analysis. So let's say you are given this molecule and you want to find out how can you synthesize this, what are the starting points. So we can consider, now this is a alpha beta unsaturated carbonyl compound, and similar to this compound, you see here, alpha beta unsaturated. But how did we get the connection? It was, we made this connection new. Remember, we made this connection by doing aldol condensation. So you can consider we can break this bond here. This is a new connection we are going to make. Also, we made the new connection between this carbon, which is this carbon right there. Right? And to begin with, what we had a carbonyl group to begin with here. And it was alpha beta unsaturated carbonyl compound here. So basically we can consider breaking this part over here. So breaking this part. And from this side you have the carbonyl group, and this is the alpha beta unsaturated carbonyl compound. This is one part, and from this part you have the carbonyl group. And then when you put these two together, first would be adding a base and then do a Michael addition, intramolecular aldol, and then removal of the water can give you this product. Similarly here, okay, so you figure out, okay, you notice this part in the molecule, and then you know, okay, so I can break the molecule from here. I can consider that I'm going to make the new connection between here and between here. Okay, so now from this is going to be alpha beta. This is the alpha beta unsaturated carbonyl compound. So this is that part. This part right there. And from the other side, this is the carbonyl group. This carbonyl group. And from here, this one going to be another carbonyl group. So when you put these two together, we can get this product made. Okay, so something to think about. See if you can do the forward reaction with the necessary steps, just for practice. Okay, now we're going to move on to another category where in this type of reactions we will see a removal of a carbon dioxide molecule. But in order to do that, we need to have certain requirements, but we'll see what are those requirements. Now the first thing is, not all the molecules be able to remove a carbon dioxide molecule. For example, alkane does not lose a proton. So this is an alkane. Now we have seen molecules losing a proton, but not alkane. Remember, in carbonyl compounds, if you have a compound like that, and then you have hydrogens like this, so these are called alpha carbons and these are alpha hydrogens. When you add a base, we had seen the base take this hydrogen and form a carb anion like that, and we just lost a proton. That's because once a proton is lost, the resulting anion is stabilized by this carbonyl group. It's not a localized negative charge. Normally, whenever you make a charge, if it is localized, if there is nothing for it to stabilize, it becomes highly unstable. It normally does not form. Same thing. So if you lose hydrogen from alkane, what you're going to get is CH3, CH2 minus. So having a negative charge on carbon and there is nothing else in the molecule to make it stable, it's very highly unlikely that it is going to happen. Meaning it's hard to remove the hydrogen from alkane. Okay, and pKa is also about 55. So the lower the pKa become more acidic, so it's easy to lose a proton. Now these hydrogens pKa, I think around 15 or so, but this is about 55, so there is a big difference. Okay, now for the same reasons you will see that carbon dioxide, so let's say you have this molecule over here. Okay, so we have, this is 1, 2, 3 propionic acid or propanoate. So you cannot lose a carbon dioxide. We have many carboxylic acid like acetic acid, CH3, COOH, pretty stable molecule, acetic acid, or you can have formic acid, and this is coming from propionic acid, propanoate. But we know that the acetic acid does not lose the carbon dioxide and become, decompose. For the same reason, if it loses a carbon dioxide by forming the anion, just like it's showing over here, if it loses this bond, then the electrons in the bond going to be on this carbon, and similar to the alkane, it would become something like that. And there is nothing for it to stabilize that carbon ion. So because of that, carbon dioxide will not lose by a carboxylic acid. Okay, there are some requirements, but we will see which molecules can lose a carbon dioxide molecule. A proton can be removed from an alpha carbon, and similarly carbon dioxide can be removed from an alpha carbon. Now in this one, I showed you in the previous slide also, if you have a carbonyl carbon, this is your alpha carbon, a base can remove this hydrogen and then that would be resonance stabilized, right? So because of that, we can form these resonance structures, meaning electrons are delocalized, so ion become more stable once the hydrogen is lost. The electrons left behind when H plus is removed are delocalized onto an oxygen. Same thing we can do removing carbon dioxide from an alpha carbon. Now remember, alpha carbon is a carbon next to a carbonyl group. Now here you have a carbonyl group in this position, and then we have a carbonate ion here, COO minus. Now we can lose this carbon dioxide molecule from this part, and then you're going to be forming carbon ion, and this carbon ion can be resonance stabilized with the carbonyl group. So we can easily remove a carbon dioxide if there is a carbonyl group in the third position to the carbon dioxide carbon atom. So this is where the carbon dioxide is going to lose. So if you number this as number 1, 2, 3. If they're in the third position, there is a carbonyl group. meaning that the negative charge is going to be delocalized throughout the carbonyl group. So then we can lose a carbon dioxide molecule. Electrons left behind when carbon dioxide is removed are delocalized onto an oxygen. It is easier to remove a proton when the carboxylic acid is in its acidic form. Acidic form is when the carboxylic acid is protonated. This form is the basic form, meaning the hydrogen is lost. Acidic form is now it is in as an acid. For example, this molecule over here, CH2, COOH. So this is the acidic form of the carboxylic acid, and then the basic form is going to be this form, O minus, when the hydrogen is removed. Now this same molecule that we have drawn, we can draw it in such a way of this molecule that it forms a 6-member transition state. Okay, so if you number these atoms, this is 1, 2, 3, 4, 5. Now I'm going to rearrange these atoms. If I rearrange and put them in a form of a 6-membered ring, I can put my alkyl group over there, number 1, and then the number 2, number 3. On the third carbon, we have a carbonyl group, and on the fourth one is an oxygen, and the fifth one is hydrogen. 1, 2, 3, 4, 5. Now, between oxygen and hydrogen, carbonyl oxygen and carboxylic acid hydrogen, and if you look like that, if it is going to complete, it's like a 6-membered ring, which makes a good transition state. So what's going to happen is now the double bond is going to take up this hydrogen and form OH there. And then the bond between oxygen and hydrogen going to break. And then the bond between these two, 2 and 3, going to break and form another bond between 1 and 2. So if you do that, what's going to happen? Now see, understand what's happening. Some bonds are going to form between oxygen and hydrogen. A bond is going to form. Do you see that? Oxygen and hydrogen, a bond is going to form. I put some dashes between that. And then this bond, 4 and 5 bond is going to break. And then oxygen 4 and the 3 is going to form a pi bond, and this bond is going to break. Okay, so let's see what we're gonna get due to this reaction. So we have R, and then on the 1 you have this group OH, and then you have this part right there on the second carbon, and then the other side we have oxygen, oxygen. Do you see that? What's happening there on the other part? Let me redraw that one. Carbon dioxide is a linear molecule, so I need to keep its geometry. Okay, now from here, so this part is going to form. Do you see that? Between 3 and 4, carbon and oxygen. This oxygen is the 4th carbon, and then this is carbon 3, and that has a oxygen. Between 2 and 3 it broke, so this is 2, and this is 1, this is 4, this is 5. So what's happening? By this process, do you see that we have generated a carbon dioxide molecule? So carbon dioxide is generated. So, and then the other part is this, I just drew. Alkyl group, and then the CH2OH. And this is a enol. This one is a enol. So it tautomerizes back to the keto form. Okay, when it tautomerizes back to the keto form, it would be this molecule RCOCH3. Okay, so you can see that how a carbon dioxide molecule can be lost when you have a third position, a carbonyl group. That's all I want you to understand from this process. So the enol, if you remember how it's gonna go back, if you have this one, CH2. So these are the tautomers that we learned earlier. This can give you, we'll also learn the mechanism. So these are keto and enol tautomers. This can be happen in the acidic medium, or it can be happened in the basic medium. Okay. Okay. So basically you get this molecule and carbon dioxide. Three oxocarboxylic acids can be decarboxylated. 3-oxocarboxylic acid. Okay, so here also similar to that. So this is 1, 2, 3. 3-oxo. So 3-oxocarboxylic acids can be decarboxylated. So 3-oxo here, carboxylic acid. Now earlier we had an alkyl group here. Now we have a OH group. So for the same thing, when you heat it up, a carbon dioxide molecule can be lost. So you form this enol and then tautomerizes to acid back, and then you are losing a carbon dioxide molecule. Okay, same process. This carbon oxygen pi bond grab the hydrogen, oxygen hydrogen bond breaks and then form carbon oxygen pi bond, a double bond, and this bond breaks. And then the driving force for this decarboxylation is the removal of a small stable gaseous molecule, carbon dioxide. Okay. Okay, here's another one. Now what would you get if you heat this up? Basically you know, so this is 1, 2, 3 3-oxocarboxylic acid. When you heat it, you basically remove this part that highlighted in yellow, and then you get this ketone. Same thing here, you have a carboxylic acid, 1, 2, 3 3-oxocarboxylic acid. You heat it and then you generate the ketone and the carbon dioxide. Okay, so just remember that when you have a 3-oxocarboxylic acid, you can get the ketone and the removal of the carbon dioxide. Okay, so we will stop here, and then we're going to use this process when we are doing the malonic ester synthesis in the next session.